This is the Hewlett-Packard 8010A pulse generator from the 70s, probably early 1970s. It's the same, is it the 4U rack mount, same size as the HP 675 you see in the background here. Found this on eBay for a very good price, and the seller very kindly made a big effort in packing it all up and sending it to me when he actually wanted me to go and pick it up. So I would like to thank him again for that. I understand he's going to watch this video and see how we get on with it. Now, it's probably not the most useful thing in the workshop, but it's such a nice looking piece of kit. And every now and then you could do with a pulse generator that's got a good response to it. I had the Philips pulse generator, which is pretty poor actually. I think it's more of a sort of like a real amateur bit of kit for just generating pulses and things. It's not particularly stable. You can't seem to get the pots to work very well. They're all a bit noisy. But this should be much better quality, obviously, because it's Hewlett-Packard. Now, it's been sold as he thinks working. I think it was sold as spares and repair, but I think he's pretty confident it works. He seems to think it maybe just needs sort of pots cleaning and things like that. It's a dual channel signal pulse generator. So basically you've got two identical channels, and if you see here, you can see it's quite clearly marked out. This is the blue channel, which is this side here, and then we've got split off to the orange channel, which is this channel here. And you can actually tie these two channels together to sort of double the pulses up and double the output power. Now, I've downloaded a manual and managed to leave that at home, so that's not going to be in this part of the video. But I think what we're going to do this evening is we will power it up and we'll have a quick look on the scope and see what it does. And then, if it all looks okay, we'll pop the cover off and give it a bit of a service. We'll clean all the controls up. It's a really nice piece of kit actually, and as we know, the Hewlett-Packard stuff usually is. And if you look at these controls here, the coarse control is on the outside, nice and positive, and you've got a fine control on the inside for, I assume, the vernier control. You've got switches here for the single and double pulse. So we've got repetition rate, pulse delay, we've got pulse width, which is basically duty cycle, which is here, transition time, which is, I assume, fall and rise time. We've got the vernier for the fall and rise time here. That's nice. These are lovely controls, feel nice. Amplitude vernier, just coming out the inside of the screen. DC offset. So basically it's pretty self-explanatory. So pulse delay, I always get a bit confused with this. I assume that pulse width is obviously duty cycle. Transition time is slope, basically slope response. Pulse delay is, I think, the dead time where between the next cycle. I'm not sure if it is repetition time is in my mind the same thing, so I need to get my head around what these two controls do. But basically it should be fairly self-explanatory once we get it on the scope and have a look. So let's power it up, plug it into the scope, the Hewlett-Packard scope. Let's see what we get on the display. Now I'm just going to turn the overhead light off to get a better idea of what's going on the screen. So what I'm going to do, it's difficult to get both the units in the. I suppose what I could do is I could set the Tektronix scope up that I've just repaired on top of it, and then we can get it all in frame. So let me come back with the Tektronix plugged in. Okay, that's the Tektronix on top. So we're going to run the Tektronix so you've got a better view. Channel 2 of the Tektronix will go to output B of the HP 8010, and channel 1 on the output A. So let's power up the HP and get that to boot. Okay, let's call up both channels. There we go. Just set our channel 2 up correctly. Set them to the same impedance and things like that, so we've got a matched output on both of them. So channel 1 is terminator is off, as is on channel 2. I've got the invert on, I'll turn that off. Okay, so we should have the same thing. So let's power this up and see what happens. So we've got a DC offset on channel 2. Check we are DC coupled on the other channel. Yep. Okay. So let's check our DC adjustment. It actually shows as turned off, so we've got a DC offset straight away on one channel. This is channel 2. They're running separate, so this we can get any waveform. So we're running on gated output, delay mode, parallel serial. Okay, I'm not entirely sure what that does. I think that's when you've got the 2 units connected together. So let's have a look. Positive going pulse. Let's see if we can get some output out of this. So the amplitude's the same. Yep, so we've definitely got a DC offset on one of the channels here. Could be the way I've set the thing up. Pulse delay is 10 microseconds. Pulse width is 10 microseconds. And we put our vernier times 1. Transition time is 10 microseconds. We're going to go for a square wave. Single pulse, double pulse. Let's try this. Here we go. Synchronization, normal or asymmetrical. Let's assume that's normal. There's our square waves. And you can see there that you've got 2 square waves. Look pretty well matched. The levels are slightly different. Just check our level adjustment. There's one channel, and there's our other channel. So we bring those into position. And the child next door is due to go to bed about this time, so as per normal it's going to scream the whole street down to let everyone know it doesn't want to go to bed, and I have to put up with it. So let's have a look. So the square wave looks working fine. Let's just check our frequencies. So cursor, let's select some cursors. Well, we're going to have time absolute, and we want percent. Units, that's it. Units we want. How do we get delta time? What function? Come on, time on channel 1. Still not au fait with these scopes. Here we go. It's got a cursor here. See that we've got a delta time of 1.5 milliseconds, which looks right. And as you can see there, the controls are actually working quite nicely. It's nicely and smooth. Let me zoom you in a bit to the scope so you can see what's happening. So this is reputation time. Works really nicely, as from what I can see there. I mean, the pots are a little bit noisy, but there's nothing horrible about them. And the rise time at the moment doesn't look that great. Let's have a look at so we can adjust the transition time. There we go. So it's going more into a triangle wave as we alter the response. That's the vernier adjustment for the amplitude. Looking good. So let's try the DC offset control. Yep, that works really well as well. So straight away it looks like this unit is actually working fine. There's a bit of a jitter here with a bit of a noisy pot, and also I'm not triggering on that channel. So let's try some of the higher frequencies. So we want a bit of triggering. So that puts a flat out. There's a little bit of difference between the two channels. I haven't actually verified the scopes correct on its outputs either, so it could be that the input of the amplifier of the oscilloscope's not perfect, but it certainly looks like it's working fine. This is the vernier adjustment for the rise and fall times. We've definitely got a very noisy pot there, so that's going to need servicing. This is the full time vernier, and for the other channel, that looks fine. So okay, we've got a little bit of noisy sort of waveform, so let's go to a pulse generation. So we'll try and bass down. And the trouble is now, because we're using a fast time base, you can't actually see the display. We can get any more brightness out of the display. Oh, come on. Okay. So there we go. So let's just go to channel 1 because we've got confusing results on with both the channels triggering at the same time. There's our trigger level. Let's go back to a square wave so we can actually see it easier. No, it's not square wave because we've got some rise time adjustments. Transition time, so we want transition time down to 10 nan. That should give us the best possible square wave. What channel am I triggering on? Come on, there we go. Triggering on channel 1. Let's move channel 2 off screen. As you can see there, even though we haven't matched it perfectly, we're getting a very fast square wave rise time. So it all looks like it's basically working fine. All it needs is a bit of a service with pots and things like that. We've got various other controls. This is double pulse. I'm not sure. Oh, it's this channel. Oh, that doesn't seem to work unless you have it on a separate mode. I'm not sure what mode that's in. This pulse delay doesn't seem to do anything, but then again, I don't know really what I'm expecting it to do anyway. So this be a pulse width adjustment. Doesn't seem to do anything. Maybe that's only on when you've got it on pulse, and I've got it on square wave. So let's set. There we go. Let's slow the time base down. There's a double pulse, so there's a single pulse there, and I don't know if you can see that. There's a single pulse there, double pulse, not obvious. So pulse width looks good. Pulse width now down to 10 microseconds. So on the 10 microsecond scale, it's just about taking up 10 microseconds on the time on the division, so you can see it's slightly out of calibration. Set the vernier pot on horizontal. Smack on exactly 1 microsecond. So really, this looks like this works absolutely perfectly. It just needs a bit of a service, a bit of a cosmetic clean-up. But it says a lot for the Hewlett-Packard gear, considering it's coming on 50 years old. It still works. We'll take it apart, we'll just check power supply capacitors, things like that. Give the pots and things a clean up. There's a couple of pots that feel a bit loose here, I'm not sure if that's normal or not. Clean it up and decide what I'm going to do with it. Thanks for watching. This is the top cover removed, and you can see it's point-to-point wiring, and not that typical of HP stuff. Most of the stuff I've come across is all sort of slotted board technology, you know, sort of boards plug into a motherboard. But it all looks in fairly good condition. I see they're using tantalum capacitors more or less wherever they use electrolytics, so that's reassuring because these tantalum capacitors should be pretty reliable. We'll need to check a couple of them just to make sure nothing's sort of untoward with them. As you see at the back here, these two electrolytic power supply capacitors here, and off to the back it goes to the TO3 output transistors for the linear regulator, and the output transistors are actually very hot, so I need to have a look to make sure that we're not over dissipating them for some reason. Maybe there's something's drawing a bit too much current, maybe the electrolytics are leaky or something like that. Power supply section here, as you can see, very early sort of technology really. I mean, not super early, but classic 70s technology, plated through hole technology. A couple of caps here. You can see a date code on these. Is that 71? I'm not sure. I need to check another couple of components here. Adjustments for voltage and stuff like that. This is the output stage here. This one of the channels of the output stage, and on the other side the same. We've got the manual, as I say, at home, but these are basically the all the parts that generate the actual waveform itself, and the shaping of the with the transition time and things like that, all done from this control. If you look along the side here, you can see that the pots have a few of the pots are a bit rusty. You can see that pot there and there. So that's not a problem really, though. I can put a bit of contact cleaner in those. These pots actually work very smoothly, so it's obviously hasn't caused a lot of problem. You can see underneath here, sort of the switches and things like that are all underneath. The plug-in connections are quite interesting because they're not the normal sort of thing I've come across. They're just all plugged into like pins. So we need to get some photographs of those before we start messing around with this thing too much. There's a relay there by the looks of it for changing over probably amplifier drive levels and things like that. And it's very much sort of looks from a distance like an audio amplifier with almost like a sort of push-pull stage all the way through. But of course you've got to remember this is a dual channel pulse generator, so it's going to look a bit like that anyway. I did notice when it was powered on, I don't know if you can hear this, it's not plugged in anymore. I pulled the power lead out the back, I think. Plug the power lead back in again. It's plugged in. Can you hear that? Right. Very noisy transformer lamination, so I need to check that, make sure they're tight, because that's a little bit annoying. So yeah, that's the top section. It's a bit dusty, but it's not in bad nick at all. So we'll take the bottom off and have a look. Okay, and underneath it's basically the same sort of thing. This is the identical board on the top here. We'll look up what they are tomorrow. Here's the capacitors. They're nice and cool. Selection switches for various things, and on the back here more pots and things like that from the front panel. All looks fine really, all looks clean. No obvious signs of burning, anything like that. I'm trying to find a date code on the capacitors. Not very clear what date codes are on here. No numbers obvious, so we'll have to have a hunt through so we can find some date codes on them. What's that one there? No obvious codes on that one either. But Good thing is, mainly using electrolytic tantalum, so it shouldn't be a problem. These caps will need to be checked with the capacitance checker, make sure their ESR is still good. But as you can see on the display, the unit looks like it's working fine. So the next thing will be is to service the pots, and then we'll see if we can run it through a calibration run. I'm just checking these two capacitors down here, the main electrolytics that are like the smoothing capacitors of the power supply. This is the first capacitor. I'm across it. It's supposed to be a 1500 microfarad, 50 volt. And you can see I'm connected up to the LCR. And you can see there, even though the capacitance is good, you can see that the dissipation factor is very poor. Now the capacitance, even though the capacitance is good, the dissipation factor shows that the things become a high ESR. And we can go to an ESR measurement there and have a look at what we get. It's 560 milliohm. Let's try that lower. Let's try the 1K. Yeah, so it's about 500 milliohm. For a capacitor that size, I mean, it's not great. But I'm particularly interested in the dissipation factor on this meter, and it should usually larger capacitors. This sort of value will show 0.2, 0.3, something like that. But it's not very good, and certainly at higher frequencies it's poor, which is what you tend to expect with a larger electrolytic capacitor. The dissipation factor goes down with higher frequency. I'm running at 1 kilohertz at the moment. So let's move to the other capacitor. That's here, and have a look. And the same value capacitor. And it's actually in circuit at the moment, so it's a bit confused by its dissipation factor. It's not getting an accurate reading. So we look at 120 hertz. It's showing 1.6 millifarads, so 1600 microfarad at 1.655. I mean, it's all over the place actually. So I think what I'm going to do is I'm going to leave the caps in situ, but I'm going to actually put maybe an additional capacitor across, because they don't seem to be leaky. Put some extra capacitance across there and have a look at the ripple on the scope.